Right this very second, as you sit watching this screen, the universe is unfolding in ways that defy logic, shatter expectations, and leave even the brightest minds utterly baffled. Imagine a cosmic dance so strange, so unpredictable, that it makes the wildest science fiction seem tame. Black holes spin like frenzied tops, stars vanish without a trace, and invisible forces warp the fabric of reality itself, all happening silently, invisibly, in the depths of space. And here's the thing, you're not just a spectator, you're part of this grand, mysterious theater, standing on a tiny blue dot hurtling through an ocean of enigmas. Think about that for a moment. At this exact instant, somewhere out there, a star might be tearing itself apart in a supernova explosion so powerful it outshines entire galaxies. Or perhaps a rogue planet, untethered from any sun, drifts through the void carrying secrets we can't even begin to guess. The universe doesn't wait for us to catch up. It's alive with phenomena that challenge everything we think we know. And the most thrilling part, scientists are racing to unravel these mysteries, piecing together clues that could rewrite the textbooks. That's why we're diving deep today into 25 of the most bizarre, mind-bending events unfolding right now in the cosmos. From ghostly radio signals echoing across billions of light years to planets where it rains molten metal, each one is a reminder of how little we truly understand. This isn't just a list, it's a journey to the edges of known space where the rules bend and the impossible becomes routine. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Right now, trillions of miles away, invisible messages are screaming across the cosmos, blasts of radio waves so powerful they outshine entire galaxies for mere milliseconds before vanishing without a trace. These are fast radio bursts, or FRB, and they're one of the universe's most electrifying puzzles. Picture this, a single burst releases as much energy as the sun does in 80 years, all compressed into a flicker shorter than the blink of an eye. And the strangest part, we still have no idea what's causing them. For years, astronomers dismissed these signals as glitches, cosmic static, maybe even telescope malfunctions. But then they started noticing patterns. Some bursts repeat, firing off like a celestial alarm clock. Others arrive alone, unpredictable and fleeting. One particularly infamous signal, nicknamed the Lorimer burst, traveled 7 billion light years before slamming into Earth's detectors, leaving scientists stunned. Theories range from the plausible to the downright wild. Could they be the death throes of collapsing neutron stars, the violent aftermath of black hole collisions? Or cue the chills, some form of advanced alien propulsion system, a beacon we're just beginning to decode. Here's where it gets even weirder. In 2020, researchers detected an FRB originating from inside our own galaxy, linked to a highly magnetic type of neutron star called a magnetar. Finally, a smoking gun, except not all FRBs match this explanation. Some burst with rhythmic precision like cosmic Morse code, while others defy any known astrophysical process. And then there's FRB 1212, a signal that repeats every 157 days like clockwork, hinting at an orbit around an unseen companion. What kind of cosmic dance could produce such eerie timing? The hunt for answers is heating up. Teams worldwide now scan the skies with AI-powered telescopes, racing to catch these flickers in real time. Every new burst is a clue, a piece of a puzzle that could rewrite our understanding of physics itself. Because here's the truth, FRBs aren't just random noise. They're whispers from the darkest corners of the universe, carrying secrets about matter, magnetism, and forces we've yet to name. And with each detection, we're one step closer to unraveling a mystery that might just change everything. Jupiter's Great Red Spot, a swirling tempest wider than Earth, has been the solar system's most famous storm for centuries, a crimson eye glaring from the gas giant's turbulent face. But right now, something bizarre is happening to this ancient maelstrom. Far from fading away as scientists once predicted, the storm is morphing, expanding, and defying every expectation. Recent data from NASA Juno spacecraft reveals a storm that's growing taller even as it shrinks slightly in width, like a cosmic accordion playing a tune we don't yet understand. And the deeper we look, the stranger it gets. For decades, astronomers watched the Great Red Spot slowly shrink, assuming it was on its way to vanishing like so many of Jupiter's smaller storms. Then came Juno's close flybys, armed with instruments that could peer beneath the storm's ruddy haze. What they found was staggering. The storm's roots plunge over 200 miles into Jupiter's atmosphere, far deeper than anyone guessed. That's like digging from New York City to Washington, D.C., straight down through churning ammonia clouds and hurricane-force winds. This depth might explain why the storm has endured for at least 400 years, drawing energy from hidden layers of the planet's chaotic atmosphere. But here's the twist. While the storm's width has decreased by about a third since the 1800s, it's now stretching upward, growing taller by about 8 miles per year. Think of it like a whirlpool that's getting narrower but taller, its winds accelerating as it compresses. Some researchers suggest this vertical expansion could mean the storm is absorbing smaller vortices, feeding on Jupiter's turbulent weather like a celestial predator. Others propose it's reacting to changes in the planet's jet streams, which have been speeding up mysteriously over the past decade. The most haunting question: what color is the storm really? Juno's cameras captured the Great Red Spot in wavelengths beyond human vision, revealing swirls of orange, yellow, and even blue beneath its famous ruddy veneer. The exact chemistry behind its hue remains unsolved, possibly a brew of sulfur, phosphorus, or sunlight-baked organic compounds. One theory suggests the storm acts like a colossal pressure cooker, dredging up deeper, darker material as it churns, then bleaching it red under Jupiter's relentless radiation. Every new Juno flyby sends back data that upends old assumptions. The storm isn't dying, it's evolving, twisting the rules of planetary science as it goes. And that's the real wonder here. Jupiter's Great Red Spot isn't just a weather curiosity. It's a laboratory for physics we can't replicate on Earth, teaching us how storms persist across centuries, even millennia. As the storm continues to shape-shift, one thing's certain: this crimson enigma has more secrets to spill, and we're only beginning to listen. Somewhere beyond the edge of everything we can see, a cosmic tug-of-war is underway, one so massive it's dragging entire galaxy clusters toward the unknown. Astronomers call it the dark flow, and it's as unsettling as it sounds. Imagine throwing a ball straight up, only to watch it curve sideways midair, pulled by something invisible. Now scale that up to galaxies, thousands of them, all drifting in the same direction at staggering speeds, as if the universe itself is tipping toward a hidden attractor. This isn't just strange, it's a direct challenge to everything we thought we knew about how the cosmos works. The discovery came from studying the afterglow of the Big Bang, the cosmic microwave background, which acts like a universal speedometer. By tracking how galaxy clusters move relative to this background, scientists noticed something impossible. These clusters were streaming at over 2 million miles per hour toward a single patch of space. The kicker: there's nothing there, no supercluster, no vast concentration of matter, just emptiness. Whatever's pulling them lies beyond the observable universe, in regions so distant their light hasn't had time to reach us in 13.8 billion years. Now theories abound, but each one bends the limits of physics. Some suggest it's the gravitational fist of another universe, a sibling cosmos brushing against ours in the multiverse. Others propose a relic from the Big Bang itself, a primordial defect in spacetime, a cosmic scar left over from creation, warping the fabric of reality. The wildest idea: that our universe isn't perfectly uniform after all, and the dark flow is evidence of a titanic imbalance, a lopsidedness written into the very laws of nature. Here's what keeps astronomers up at night. If the dark flow is real, it means there's something out there so colossal it defies the cosmological principle, the idea that the universe should look roughly the same in all directions. And that upends centuries of astronomy. Current telescopes can't see far enough to confirm it, but upcoming missions like the European Space Agency's Euclid might finally crack the case. Until then, the dark flow remains one of cosmology's greatest riddles, a reminder that the universe isn't just expanding, it might be running toward something. And we have no idea what that something is. One of the most baffling cosmic performances in recent memory came from a familiar face in the night sky: Betelgeuse, the fiery shoulder of the constellation Orion. Normally a steady beacon, this red supergiant suddenly dimmed in late 2019, losing nearly 2/3 of its brightness in a matter of months. For stargazers and scientists alike, it was like watching a porch light flicker and fade, sparking whispers of an impending supernova. But Betelgeuse wasn't dying, it was pulling a cosmic sleight of hand, and we're still unraveling the trick. At roughly 1,000 times the size of our Sun, Betelgeuse is the kind of star that doesn't do anything quietly. Its usual pulsations, swelling and shrinking over cycles of hundreds of days, have been documented for centuries. But the Great Dimming event was something entirely different, an unprecedented drop that left astronomers scrambling for explanations. Telescopes trained on the star revealed a chilling sight. Its southern hemisphere had darkened dramatically, as if a shadow had fallen across its surface. The leading theory, a colossal belch of stellar material. Betelgeuse likely ejected a vast cloud of superheated gas and dust, which cooled into a cosmic veil, obscuring its own light from our perspective. Imagine a candle suddenly shrouded by its own smoke. Then, just as mysteriously, Betelgeuse brightened again, but not before igniting a firestorm of speculation. Could this be the prelude to a supernova? After all, this star is a ticking time bomb, expected to explode within the next 100,000 years, a blink in cosmic terms. A nearby supernova would be a once-in-human-history event, visible even in daylight for weeks. But here's the twist: Betelgeuse's dimming wasn't the signature of a star on the brink. Instead, it offered a rare peek into the chaotic life of a supergiant. These stars are messy, unstable behemoths, shedding entire suns' worth of mass in erratic outbursts. The dimming wasn't a death rattle, it was a temper tantrum. What's truly unsettling is how little we understand about Betelgeuse's inner workings. Cutting-edge simulations suggest its dimming might have been caused by convective currents, massive bubbles of plasma rising from its core like boiling water in a pot, triggering localized cooling. Others propose magnetic upheavals or even the formation of starspots, dark patches far larger than anything our Sun could produce. And let's not forget the wild card. Gravitational waves detected around the same time raised eyebrows, though no direct link to Betelgeuse was proven. Now, Betelgeuse is back to its usual tricks, pulsing and flickering like nothing happened. But that's the beauty of this cosmic enigma. It's a reminder that the universe loves a good plot twist. Whether it's dust, plasma, or something we haven't even considered, Betelgeuse's great dimming taught us one thing: even the stars we think we know best can still surprise us. And when this giant does finally go supernova, well, let's just say you'll want front row seats. Saturn isn't just the solar system's ringed jewel, it's home to one of the strangest weather patterns ever observed. High above the planet's north pole, a gargantuan hexagon spins with eerie precision, a six-sided hurricane large enough to swallow 4 Earths whole. This isn't some fleeting atmospheric quirk. It's a permanent feature, raging for at least 40 years since Voyager first spotted it in the early 1980s. And the more we study this geometric tempest, the more it defies every rule of planetary science. At first glance, the hexagon looks artificial, as if some cosmic architect etched a perfect polygon into Saturn's cloud tops. Each side stretches nearly 9,000 miles, with blistering jet streams racing along its edges at over 300 miles per hour. Unlike Earth's chaotic weather systems, this structure maintains razor-sharp angles even as it rotates, spinning in sync with Saturn's deep interior like a gear in a planetary clockwork. The real shock came when Cassini's infrared cameras peered beneath the haze, revealing the Hexagon extends hundreds of miles downward, a towering atmospheric skyscraper of churning ammonia and hydrogen. So how does a storm, a phenomenon synonymous with chaos, lock into such rigid geometry? Laboratory experiments offer tantalizing clues. When scientists spin fluids at high speeds in controlled settings, they can produce similar polygonal shapes, hinting that Saturn's hexagon might emerge from deep-rooted turbulence interacting with the planet's rapid rotation. Picture honey poured onto a spinning plate. The viscous fluid can form stable waves, and Saturn's atmosphere might be doing the same on a planetary scale. But here's the catch: no model perfectly replicates the hexagon's stability or its precise six-sided symmetry. Earth's hurricanes dissipate within weeks. This storm has outlasted generations of researchers. Theories abound, each raising new questions. Some suggest the hexagon acts like a standing wave, anchored by Saturn's internal magnetic field. Others propose it's a colossal version of what happens when you swirl water in a cup. Except Saturn's cup is a 60,000-mile-wide polar vortex. Then there's the wild card. Could the hexagon's stability be tied to Saturn's mysterious inner heat, which radiates more energy than the planet receives from the distant sun? The hexagon's shadowy counterpart, a matching polar vortex at the South Pole, swirls in a traditional circular pattern, deepening the puzzle further. Perhaps the most haunting detail comes from the hexagon's eye. At its center lies a smaller, circular storm that churns like the calm center of a terrestrial hurricane, except this calm is relative, with winds still howling at hundreds of miles per hour. During Saturn's northern summer, sunlight revealed the hexagon's shifting color, its azure center darkening to a deep gold, suggesting seasonal changes we're only beginning to decode. What makes the hexagon so mesmerizing isn't just its strangeness, it's the way it forces us to rethink atmospheric physics altogether. On Earth, we categorize storms as temporary disruptions. But Saturn's hexagon is a permanent institution, a reminder that nature's rulebook has chapters we haven't even opened. Until we send another mission to this ringed giant, this six-sided enigma will keep spinning, silent and steadfast, daring us to unravel its secrets. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there. A tiny, tumbling object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed visitor from interstellar space. But this wasn't just any cosmic rock. Its bizarre behavior sparked a firestorm of debate, dividing scientists and even fueling whispers of extraterrestrial origins. Because Oumuamua didn't just pass through, it accelerated, as if pushed by an invisible hand. At first glance, Oumuamua seemed ordinary, a reddish, elongated chunk roughly a quarter-mile long, tumbling end over end. But the closer researchers looked, the stranger it became. Most asteroids follow predictable paths dictated by gravity, yet Oumuamua sped up slightly as it left the inner solar system, a trait typically seen in icy comets as their frozen gases heat up and vent. Except Oumuamua showed no coma, no telltale cloud of gas or dust. Its surface appeared unusually reflective, almost metallic, and its shape, somewhere between a cigar and a pancake, was unlike any natural object we'd seen. The scientific community split into camps. One side argued Oumuamua was a rare type of dark comet, a frigid body that vents hydrogen gas, leaving no visible trail. Others proposed it was a shard of a Pluto-like world, sheared off in some ancient collision and sent careening across the galaxy. Then came the wild card, Harvard astrophysicist Avi Loeb's controversial suggestion that Oumuamua's acceleration and odd proportions might hint at an artificial origin, perhaps a light sail propelled by starlight, a discarded piece of alien technology. The debate raged because Oumuamua defied easy classification. Traditional comets spewed dust and gas when warmed by the sun, creating a visible tail. Oumuamua's acceleration was subtle, almost stealthy, as if whatever was pushing it left no trace. Later studies suggested outgassing could still explain its speed boost. If the vented material was pure hydrogen or carbon monoxide, it might have been invisible to telescopes. But the real frustration, we'll never know for sure. Oumuamua moved too quickly, and we detected it too late, catching only a fleeting glimpse before it vanished into the void. What lingers isn't just the mystery of Oumuamua's identity, but the tantalizing possibility that interstellar space might be teeming with such objects, silent travelers carrying secrets from distant star systems. Future telescopes like the Vera Rubin Observatory aim to catch more of these visitors early, giving us time to study them properly. Until then, Oumuamua remains a cosmic Rorschach test, a fleeting enigma that reveals as much about our curiosity as it does about the universe's hidden diversity. Was it a comet, an asteroid, or something beyond our current understanding? The answer, much like Oumuamua itself, is still out there. Deep in the heart of distant galaxies, supermassive black holes aren't just consuming matter. They're belching it back out with enough force to reshape entire cosmic neighborhoods. Astronomers call these violent outbursts black hole burps, and they're among the most baffling behaviors in the universe. Picture a cosmic toddler swallowing its meal only to spit half of it across the room, except here, the toddler is millions of times the mass of our sun, and its tantrums can fling superheated plasma across thousands of light years. These aren't random eruptions. Observations from telescopes like Chandra and Hubble reveal that black holes often wait years, sometimes decades after a feast before launching these staggering jets of energy. The delay is what stumps scientists. Why would a black hole linger before violently expelling material it already pulled in? One leading theory suggests it's all about the buildup. As gas, dust, and stars spiral toward the black hole's event horizon, they don't just vanish instantly. Instead, they form a swirling, superheated disk, a kind of cosmic whirlpool where magnetic fields twist and snap like rubber bands. When the tension becomes too great, the black hole ejects a fraction of the infalling matter in opposing jets, punching through galaxies at nearly the speed of light. But here's where it gets stranger. Some of these jets don't fire straight. They wobble, precess, or even curve dramatically, as if the black hole itself is stumbling. In 2022, astronomers watched a jet from galaxy M87 home to the first ever imaged black hole, bend like a garden hose spewing water. The culprit, maybe the black hole's spin, is misaligned with its accretion disk, creating a wobbly top effect. Or perhaps the jets are plowing through dense interstellar gas, sculpting them into bizarre shapes. Either way, these bent jets suggest black holes are far messier eaters than we imagined. The most mind-bending detail, these outbursts might be cosmic recycling programs. The ejected material, rich in heavy elements, can trigger star formation in distant regions, seeding future generations of solar systems. So while a black hole's burp might obliterate anything in its immediate path, it could also be fertilizing the universe for new life. Talk about a destructive creator. What we're witnessing isn't just chaos, it's evidence that black holes are active participants in galactic evolution, not just passive destroyers. Every jet, every delayed eruption, forces us to rewrite the playbook on how these monsters shape the cosmos. And with upcoming telescopes like the James Webb studying these events in infrared, we're on the brink of decoding why black holes don't just consume. Sometimes they give back violently. Every second, trillions of ghostly particles pass straight through your body and the entire Earth without leaving a trace. These are neutrinos, the universe's most elusive cosmic messengers, and the ones arriving from deep space carry energies so immense they dwarf anything produced in our most powerful particle colliders. Dubbed astrophysical neutrinos, these high-speed phantoms are the fingerprints of the universe's most violent events, yet their origins remain one of modern astronomy's greatest hunts. Unlike light, which can be blocked or distorted by dust and magnetic fields, neutrinos travel unimpeded across billions of light-years, delivering pristine information about their cataclysmic births. The catch: they barely interact with matter at all. Detecting them is like trying to catch a bullet with a butterfly net in total darkness. That's why instruments like IceCube, a massive detector buried deep in Antarctic ice, rely on sheer volume. When a rare neutrino does collide with an atom, it creates a faint blue flash called Cherenkov radiation, revealing its direction and energy. In 2013, IceCube made history by catching the first confirmed high-energy neutrinos from beyond our galaxy, each packing the punch of a major league fastball in a single subatomic particle. But here's the twist: tracing these neutrinos back to their sources is like following a breadcrumb trail that vanishes behind you. While some have been linked to flaring blazars, supercharged black holes shooting jets directly at Earth, others point to empty patches of sky, hinting at hidden cosmic accelerators we've yet to identify. One leading suspect: tidal disruption events, where stars ripped apart by black holes unleash particle beams capable of forging neutrinos. Another contender: supernova wrapped in thick dust clouds, invisible to telescopes but leaking neutrinos like steam from a pressure cooker. The most tantalizing clue came in 2017, when a neutrino alert prompted telescopes to swivel toward a blazar 4 billion light-years away, caught in the act of spewing gamma rays. It was a smoking gun, proof that these ghostly particles could help solve the century-old mystery of where cosmic rays, high-energy protons bombarding Earth, originate. Yet even this breakthrough raised new questions. Why do some neutrinos arrive in bursts while others trickle in sporadically? Could there be entirely new classes of objects, dark, neutrino-only factories lurking undetected? What makes neutrinos so thrilling isn't just their mystery, but their potential to rewrite astrophysics. They're silent witnesses to processes no telescope can see, from the hearts of collapsing stars to the annihilation of dark matter. Future detectors like the planned IceCube Gen 2 aim to catch 10 times more neutrinos, painting a sharper portrait of the invisible universe. Until then, every flash in the ice is a cipher, a whisper from the cosmos's most shadowy corners waiting to be decoded. Between the glittering threads of galaxy clusters and superclusters stretch deserts of nothingness, so vast they could swallow our entire local group of galaxies without a trace. These are cosmic voids, regions of space spanning hundreds of millions of light-years where galaxies are nearly absent, and matter is so sparse it defies the very laws of probability. Imagine standing in the middle of one. You'd see only a handful of stars in any direction, their light stretched thin across an ocean of emptiness. But here's the chilling part: according to our best cosmological models, voids this large and barren shouldn't exist at all. The discovery of these voids came as a shock to astronomers mapping the universe's large-scale structure. Surveys like the Sloan Digital Sky Survey revealed a cosmic web, a labyrinth of galaxy filaments surrounding bubble-like voids, but the sheer scale of these empty regions shattered expectations. The largest, the Oddities void, spans 330 million light-years and contains just 60 galaxies. To put that in perspective, our Milky Way's neighborhood would pack thousands of galaxies into the same volume. It's as if someone carved out a sphere of space and erased almost everything inside, leaving behind a ghostly residue. Why does this emptiness unsettle scientists? Because the standard model of cosmology, built on decades of observations, predicts matter should distribute more evenly after the Big Bang's initial fluctuations. Quantum mechanics suggests tiny density variations in the early universe grew over time, forming the web we see today. But voids like Oddities are too big, too empty. Their existence implies gaps in our understanding of dark energy, gravity, or the universe's infancy. Some theorists propose these voids are remnants of prehistoric sound waves from the Big Bang, frozen in space-time. Others speculate they're evidence of exotic physics, like dark matter interactions we haven't yet imagined. The eeriest voids aren't just empty, they're growing. Dark energy, the mysterious force accelerating the universe's expansion, works fastest where matter is scarcest, causing voids to inflate like balloons. One day, distant voids may merge into a single, all-consuming emptiness, stretching space until even light from neighboring galaxies can't reach us. But right now, they're cosmic laboratories. The near-perfect vacuum inside voids lets scientists study phenomena impossible to observe elsewhere, like the faint imprint of primordial magnetic fields or the true nature of quantum vacuum energy. Perhaps the most haunting lesson of these voids is humility. They remind us that what we call the universe, the glittering galaxies, the swirling nebulae, is just the froth on an ocean whose depths we've barely glimpsed. And as telescopes probe ever larger swaths of sky, each new void whispers the same question. How much of the cosmos is missing from our maps? The answer might rewrite physics itself. Lighthouses don't just vanish unless they're in space. Meet PSRB 1931+24, a pulsar that doesn't pulse steadily like its cosmic cousins. Instead, this spinning stellar corpse winks on and off like a malfunctioning beacon, staying silent for years before suddenly roaring back to life. Discovered in 2006, this celestial enigma behaves unlike any other pulsar we've observed, flipping between on and off states with no discernible pattern. When active, it blasts out radio waves every 1.35 seconds with atomic clock precision. Then, without warning, it shuts down completely, plunging astronomers into years of radio silence before reigniting like nothing happened. The strangeness runs deeper than its erratic schedule. Most pulsars, the ultra-dense remnants of supernova explosions, rotate with unwavering stability, their electromagnetic beams sweeping past Earth like cosmic metronomes. But PSRB 1931+24's disappearances suggest something is interfering with its ability to generate those beams. The leading theory, its magnetic field, the engine powering its emissions, might be temporarily switching off. Picture a light bulb with a frayed wire flickering unpredictably as the connection comes and goes. Except here, the wire is a magnetic field trillions of times stronger than Earth's, and the flickering lasts for epochs. Here's what makes it even weirder. When this pulsar reactivates, it spins slightly slower than when it stopped, as if something braked it during its silent phase. That shouldn't happen. Pulsars typically slow down gradually as they radiate energy, like a spinning top winding down. But this one seems to lose extra momentum only when it's off, hinting at an unseen drag, perhaps winds of charged particles escaping during dormancy, or a previously unknown interaction between the pulsar's crust and its superfluid interior. Some researchers speculate its magnetosphere, the zone dominated by its magnetic field, might be collapsing and reconfiguring in cycles like a cosmic reboot. Then there's the timing. The pulsar's on phases last roughly 30 to 40 days, while its off periods stretch for years. Why this rhythm, no one knows. It's too irregular to be orbital. No companion star or planet has been found to disturb it. Could it be internal? Pulsars are thought to have crystalline crusts floating atop oceans of superfluid neutrons. Cracks or quakes in this exotic matter might trigger the shutdowns. Or maybe, as one provocative paper suggested, the pulsar's magnetic poles are migrating across its surface, temporarily pointing away from Earth. What's at stake isn't just one oddball pulsar. If more of these intermittent pulsars are out there, they could rewrite our understanding of how these cosmic lighthouses work. Current models assume pulsars are stable until they eventually fade, not that they take decade-long naps. Future radio telescopes like the Square Kilometre Array could scan the skies for similar objects, revealing whether PSRB 1931+24 is a freak accident or a sign of hidden diversity among stellar remnants. Until then, this winking enigma serves as a reminder. Even the most predictable corners of the universe can still throw us a curveball, and when they do, the rules, just like this pulsar's beam, might flicker out entirely. Right now, an invisible storm is barreling through our cosmic neighborhood, a hurricane of dark matter tearing through the Milky Way at 500,000 miles per hour. Scientists call it S1, a relic stream left over from a cannibalized dwarf galaxy, and it's passing straight through Earth's backyard. Unlike ordinary matter, this stuff doesn't reflect light, block light, or collide with atoms. It's utterly silent, completely intangible, yet its gravitational fingerprints are rewriting the rules of the hunt for the universe's most elusive substance. This isn't just another wisp of dark matter. S1 is a concentrated tidal stream, a cosmic river of particles siphoned off a smaller galaxy devoured by the Milky Way billions of years ago. Normally, dark matter is thought to drift in a diffuse halo around galaxies, but S1's debris is packed so densely that models suggest it could deliver 20 times more particles to Earth's detectors than typical dark matter winds. Picture standing in a sandstorm versus a hurricane. That's the difference, and for physicists that density is a golden opportunity. If dark matter interacts with ordinary matter at all, even faintly, this surge should make it easier to spot. The real twist: S1's particles might not behave like the dark matter we've been searching for. Most experiments, like those deep underground in abandoned mines, hunt for WIMP, weakly interacting massive particles, hypothetical heavy entities that barely graze ordinary atoms. But S1's debris could include something wilder: actions, ultralight particles that act more like waves than discrete bullets. These could transform in magnetic fields into detectable photons, leaving faint microwave signatures. Others speculate the stream might contain mirror matter, a shadowy twin to our own atoms that barely acknowledges our universe's laws. Here's where the plot thickens. In 2018, researchers noted that S1's trajectory aligns eerily with unexplained signals in multiple experiments. The Dharma/Libra project in Italy has recorded annual modulation, a seasonal wobble in particle detections for decades, a pattern some argue could match Earth moving through S1's current. Meanwhile, the Xenon 1T detector briefly spotted an excess of electron recoils in 2020, a blip that might fit certain action models. Skeptics counter that background noise or equipment quirks could explain both anomalies, but the timing is provocative. The hunt is heating up. Next-generation detectors like LUX Zeppelin and the upcoming IOXO are tuning their instruments specifically for S1's predicted signatures. Even if this dark matter hurricane slips through unnoticed, its passage forces us to confront a humbling truth. After decades of searching, we're still guessing what dark matter looks like. S1 isn't just a scientific opportunity, it's a cosmic litmus test, proving that the universe's secrets don't give themselves up easily. And if we do catch a whisper from this invisible storm, it might finally crack open the darkest chapter in modern physics. Out in the cosmic darkness, far from the warmth of any star, lonely worlds drift through the void like misplaced marbles, orphan planets untethered to any solar system. These rogue planets, some larger than Jupiter, wander entirely alone, unlit by a sun's glow and unseen except for the faint heat they emit. Astronomers once thought such free-floating worlds were rare anomalies, but recent surveys suggest there could be billions of them in our galaxy alone, outnumbering stars by a staggering margin. And their existence throws a wrench into everything we thought we knew about how planets are born. Take MOA 2011 BLG 262, for instance, spotted in 2011 by gravitational microlensing. a phenomenon where the planet's gravity briefly magnifies the light of a distant star behind it. This rogue was the first Earth mass world discovered floating freely through interstellar space. But here's the kicker: it shouldn't exist. Traditional planet formation theory says worlds coalesce from the dusty disks surrounding young stars, slowly growing over millions of years. So how did this one escape? One possibility is violent ejection, a gravitational slingshot from a chaotic young system, flinging planets into the abyss like cosmic pinballs. Simulations show that in systems with multiple giant planets, gravitational tugs of war can send one or more careening into the void. Yet some rogue planets defy even this explanation. Take the tiny Jupiter mass object OTS-44, drifting just 500 light-years away. Unlike most rogue giants, which are cold and ancient, this one is young, just 2 million years old, and still glowing with the heat of its formation. It's too young to have been ejected from a star system. It may have formed on its own, collapsing directly from a gas cloud like a failed star. This raises a radical idea. Maybe not all planets need stars. In the darkest, coldest corners of molecular clouds, pockets of gas might condense into planet-sized objects, bypassing the traditional stellar nursery entirely. Then there's the real head-scratcher, ultra-diffuse rogue planets. In 2020, astronomers using radio telescopes detected a bizarre object in the TW Hydra Association, a free-floating body with the density of a marshmallow, its gravity barely strong enough to hold itself together. Some speculate it's the shattered remnant of a gas giant, ripped apart by a close encounter with a black hole or neutron star. Others wonder if it's something entirely new, a class of puffy planets born from exotic physics we haven't yet imagined. The hunt for these cosmic nomads is accelerating. Projects like the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will scan for microlensing events on an unprecedented scale, potentially revealing thousands more rogues. Each discovery peels back another layer of mystery. Are these worlds sterile wastelands, or could some, heated by internal radioactivity or tidal forces, harbor subsurface oceans, even life? If planets can form or survive untethered to stars, the galaxy's habitable real estate might be far vaster than we ever dreamed. One thing's certain: rogue planets are more than celestial oddities. They're forcing us to rewrite the story of planetary birth, proving that the universe has more ways to build a world than we ever imagined. And with every new free-floating discovery, we're reminded that the cosmos loves to break its own rules, leaving us to piece together the clues. In the chaotic aftermath of a supernova, when a massive star collapses into an unimaginably dense neutron star, sometimes nature hands us a cosmic wild card, the magnetar. These aren't just ordinary neutron stars. They're the universe's ultimate magnetic monsters, with fields so strong they could strip the atoms right out of your body from 1,000 miles away. But the real showstopper, their occasional violent glitches, sudden, unpredictable changes in spin that unleash enough energy to shake spacetime itself. Picture a spinning top, smooth and steady until it hits a crack and lurches violently. That's a magnetar glitch. These stars rotate at blinding speeds, some completing a full turn in mere seconds, their surfaces locked into rigid crusts of neutron-rich material. But beneath that crust lies a surreal ocean of superfluid neutrons, flowing with zero friction. When the crust and the core fall out of sync, often due to stresses from the magnetar's own ridiculously powerful magnetic field, the star's spin can abruptly change. In a fraction of a second, its rotation might speed up by a fraction, or in extreme cases, slow down like a cosmic record scratch. The energy released during these glitches is staggering. In 2004, the magnetar SGR 1820-20 unleashed a burst so powerful it briefly ionized Earth's upper atmosphere from 50,000 light-years away. That's like a flashlight on Neptune flickering and making your hair stand on end. The event was so intense it saturated orbiting detectors, forcing scientists to reconstruct the data from the overspill. And here's the kicker. We still don't fully understand why some glitches come with apocalyptic energy releases while others pass silently, detectable only by ultra-precise pulsar timing networks. One leading theory involves starquakes. Magnetocrusts are under unimaginable strain, stretched and squeezed by magnetic fields a quadrillion times stronger than Earth. When the crust finally cracks, releasing pent-up energy like a snapped rubber band, it might trigger a glitch. But other magnetars glitch without detectable starquakes, suggesting the superfluid interior is the real puppeteer. As this exotic fluid vortices twist and reconnect, it might transfer angular momentum to the crust, yanking the star's spin rate in unpredictable ways. Then there's the wild card, magnetic field evolution. Magnetars don't just have strong fields, their fields are dynamic, decaying over centuries in fits and starts. Some researchers argue that sudden magnetic rearrangements could twist the crust like a pretzel, forcing a glitch. Supporting this idea, a few magnetars have been caught switching off their X-ray emissions post-glitch, as if their internal magnetic plumbing underwent a seismic overhaul. The most unsettling part, glitches might be warnings. Several magnetars, including the infamous SGR 1900+14, have exhibited pre-glitch whispers at tiny changes in spin rate or X-ray output, hinting at impending turmoil. If we can decode these patterns, we might one day predict magnetar outbursts the way we forecast earthquakes. Until then, these glitching behemoths remain cosmic roulette wheels, spinning silently until, without warning, they rewrite the rules of physics in a blink. And with every new glitch, they dare us to unravel a mystery where gravity, quantum mechanics, and magnetism collide in ways we're only beginning to fathom. If you took every star, every planet, and every speck of dust in the observable universe and weighed it all, you'd only account for about half of the matter that should exist. That's the universe's missing matter problem, a cosmic accounting error so glaring it's kept astrophysicists awake for decades. We're not talking about dark matter here. This is regular matter, the protons, neutrons, and electrons that make up everything from galaxies to coffee cups, and according to the best models of the Big Bang, about half of it has simply vanished. So where did it go? The leading suspect, vast, diffuse webs of superheated gas strung between galaxies, too faint to see with traditional telescopes. Picture steam rising from a cup of coffee, but on a cosmic scale, filaments of million-degree hydrogen and helium stretching across millions of light years. These intergalactic threads, predicted by supercomputer simulations, should contain the bulk of the missing atoms. The challenge, they're nearly transparent. Unlike stars or dust clouds, this gas doesn't absorb or emit much light, making it the ultimate cosmic hide-and-seek champion. Then there's the warm, hot intergalactic medium, or WIM, a ridiculous acronym for an even more ridiculous idea. This is matter so hot it's been ionized, stripped of electrons, and stretched so thin that a cubic meter of it might hold just a single atom. In 2018, astronomers finally caught a glimpse of the WIM using distant quasars as backlights. As the light from these ultra-bright galactic cores passed through the invisible gas, certain wavelengths were subtly absorbed, revealing oxygen atoms lurking in the cosmic fog. It was like finding fingerprints on a window you didn't realize was there, but the plot thickens. Even after accounting for these faint structures, the numbers still don't quite add up. Some of the missing matter might be hiding in plain sight, disguised as ultra-diffuse galaxies, ghostly collections of stars so sparse they're virtually see-through. Others speculate it's tied up in rogue black holes or exotic particles we've yet to detect. The most mind-bending theory, a fraction could be locked inside alternate dimensions, leaking out of our observable universe entirely. The hunt for this lost matter isn't just bookkeeping, it's a test of our entire understanding of cosmic evolution. Upcoming missions like the European Space Agency's Athena X-ray Observatory aim to map these hidden reservoirs in unprecedented detail, scanning for the faint X-ray whispers of superheated gas. Every atom found brings us closer to solving one of cosmology's greatest puzzles. If we can't even account for the ordinary stuff, how will we ever tackle the truly mysterious, like dark matter or dark energy? The universe, it seems, is still holding onto its receipts, and until we find them, our cosmic ledger will remain stubbornly unbalanced. Far out in the constellation Cygnus, a star named KIC 8462852, better known as Tabby's star, behaves like no other. Most stars dim predictably when planets pass in front of them. Their light curves smooth and rhythmic, but this one flickers and dips erratically, sometimes losing up to 22% of its brightness in ways that defy conventional explanations. Discovered in 2015 by citizen scientists combing through Kepler Space Telescope data, Tabby's star has become the Rosetta Stone of cosmic oddities, spawning theories so wild they straddle the line between astrophysics and science fiction. At first, astronomers assumed the culprit was a swarm of comets, thousands of them, orbiting in tight formation, their dusty tails blotting out the star's light in chaotic patterns. But comets couldn't explain the star's long-term dimming, a gradual fade of nearly 3% per century. Then came the jaw-dropper. Some of the dips were asymmetrical, as if whatever was blocking the light wasn't a sphere, but something jagged or uneven. That's when the phrase alien megastructure entered the conversation. Could this be evidence of a Dyson swarm, a hypothetical shell of energy collecting panels built by an advanced civilization? The idea wasn't entirely fringe. Even renowned astronomers like Jason Wright of Penn State argued that while unlikely, it was worth considering when all natural explanations fell short. But the plot thickened with later observations. The star's infrared emissions didn't match what you'd expect from a megastructure which should radiate waste heat. Instead, the data pointed to fine dust microscopic particles scattering starlight in bizarre ways. By 2018, Hubble and follow-up studies confirmed the presence of circumstellar dust, though its origin remained murky. Was it the debris of a shattered moon, a collision between planet-sized bodies, or perhaps a disintegrating super-Earth, its rocky corpse trailing a vast, uneven cloud? The most compelling twist came in 2021, when astronomers noticed the dips varied depending on the wavelength of light observed. Blue light dimmed more than red, a telltale sign of tiny particles, not solid objects. This ruled out monolithic megastructures but deepened the puzzle. Why would dust behave so erratically? Some proposed a massive, tilted ring system around an unseen planet, casting shadows as it wobbled. Others suggested a rogue planet with a superheated comet-like tail, vaporizing as it plunged perilously close to the star. Now the focus has shifted to the star itself. Tabby's star is an F-type main sequence star, slightly hotter and more massive than the Sun, but its spectrum shows odd chemical signatures, including fleeting traces of lithium. Could it be recovering from a recent planetary collision, its atmosphere still laced with debris, or is it harboring a hidden companion, a brown dwarf or black hole stirring up chaos in its vicinity? The real lesson of Tabby's star isn't just about solving a single mystery. It's about how science grapples with the unknown. Every time one theory crumbles, another rises, each more nuanced than the last. From comet swarms to cosmic construction sites, each idea pushes the boundaries of what we consider plausible. And as new telescopes like the James Webb peer closer, one thing's certain: this star isn't done keeping us guessing. Whether the answer lies in exotic astrophysics or something stranger still, Tabby's star remains a beacon not just of light, but of the endless surprises the universe has in store. The universe isn't just a scattering of galaxies, it's a vast, intricate spiderweb, with threads of dark matter weaving through the emptiness, binding everything together in a cosmic tapestry. These filaments, part of what astronomers call the cosmic web, form the scaffolding of the universe, guiding where galaxies form and how they move. But here's the twist: this web is invisible. We can't see it, touch it, or even detect it directly. Yet its gravitational fingerprints are everywhere, shaping the largest structures in existence with the subtle pull of its ghostly threads. Picture the universe a few 100 million years after the Big Bang. Tiny fluctuations in density, ripples from the birth of spacetime itself, began collapsing under gravity's grip. Dark matter, that mysterious substance making up 85% of the universe's mass, clumped first, forming an immense network of tendrils. Ordinary matter, the stuff of stars and planets, flowed along these invisible highways, pooling at the intersections like dew on a spider's web. Over billions of years, these knots grew into galaxy clusters, while the filaments between them stretched across millions of light years, thin and diffuse but unimaginably massive. The first direct evidence of this web came in 2012, when astronomers used the light of a distant quasar as a backlight to illuminate a single filament. Like shining a flashlight through fog, they detected the faint glow of hydrogen gas tracing the dark matter's path, a thread of the cosmic web caught in silhouette. Since then, sophisticated simulations like the Millennium Run have mapped this structure in breathtaking detail, revealing a universe far more connected than we ever imagined. The filaments aren't static, they vibrate with galaxies streaming along them, pulled by gravity in a slow-motion dance that's been ongoing for 13 billion years. What's truly bizarre is how these filaments behave. Some are as narrow as a few million light-years across cosmic tightropes stretched between galaxy clusters. Others fan out into vast sheets like the Great Wall, a structure so colossal it defies the very notion of scale. The most unsettling part: we're inside this web right now. The Milky Way sits on the fringes of the Laniakea supercluster, a sprawling network of galaxies being pulled toward a gravitational nexus nicknamed the Great Attractor. Every galaxy, every star, even our own planet is caught in this invisible current, drifting toward something we can't fully see. The cosmic web doesn't just connect galaxies, it feeds them. Along these filaments, rivers of gas flow into hungry galactic centers, fueling the birth of new stars. Supermassive black holes at the hearts of galaxies gorged on this intergalactic bounty, growing to sizes that shouldn't be possible. Without these dark matter highways, the universe as we know it wouldn't exist. Galaxies would be isolated islands adrift in a featureless void, yet the web's full nature remains elusive. Is it perfectly uniform, or are there gaps, voids where the threads snap? Some theories suggest that dark matter itself might interact in ways we don't yet understand, clumping or dispersing in patterns that could rewrite cosmology. Upcoming telescopes like the Euclid space mission aim to map the web in 3 dimensions, tracing its evolution across cosmic time. What's clear is this: the cosmic web is more than just structure. It's the universe's circulatory system, its nervous system, its architecture, and its fate all woven into one. And as we peer deeper into its threads, we're not just studying the cosmos, we're learning how to read the blueprint of existence itself. Somewhere in the depths of intergalactic space, a cosmic fugitive is on the run, a supermassive black hole weighing as much as 20 million suns, hurtling through the void at breakneck speed. This isn't science fiction, it's a real-life discovery that's left astronomers baffled. In 2023, the Hubble Space Telescope spotted something unprecedented: a black hole fleeing its home galaxy, dragging behind it a 200,000 light-year-long contrail of newborn stars, like a celestial jet trail glowing in the darkness. This rogue black hole didn't just wander off quietly, it was violently evicted. The leading theory suggests a cosmic collision was to blame. When 2 galaxies merged, their central black holes spiraled inward, locked in a gravitational dance. But instead of merging smoothly, a third black hole might have joined the fray, disrupting the delicate balance. The resulting gravitational kick was so powerful it sent one of the black holes careening outward at speeds exceeding 4 million miles per hour. Picture a game of cosmic billiards where the cue ball smashes into the others, sending one flying off the table entirely. What makes this runaway so bizarre isn't just its speed, it's the trail of stars left in its wake. Typically, black holes are destroyers, not creators, but as this one tore through intergalactic gas, it compressed the material in its path, triggering star formation. Like a plow churning the soil, the black hole's gravitational wake became a stellar nursery, glowing with the light of millions of young blue stars. It's the ultimate cosmic irony, an object known for devouring light inadvertently sparking it. The most puzzling part, we've never seen anything like this before. Black hole ejections have been theorized for decades, but actual evidence was scarce. Some models suggested they'd be dark, invisible, moving too fast to leave a trace. Yet here we have one lighting up the cosmos like a flare in the night. Could there be others out there, invisible because they're not plowing through dense gas? Or is this a freak occurrence, a perfect storm of galactic chaos? Future telescopes like the Nancy Grace Roman Space Telescope will scan for more of these renegades, potentially rewriting our understanding of black hole dynamics. Because if supermassive black holes can be hurled into the void, what else might be lurking in the shadows, unseen, untethered, and utterly unpredictable? This runaway isn't just an anomaly, it's proof that even the universe's most monstrous forces can still surprise us. Deep in the afterglow of the Big Bang, a cosmic cold spot lingers like a bruise on the fabric of the universe, an anomaly so vast and unexplained it has astronomers questioning the very foundations of cosmology. This eerie chill, spanning nearly 2 billion light-years across the cosmic microwave background, is colder than its surroundings by about 70 microkelvins, a tiny difference on paper, but a glaring red flag when mapped against the otherwise smooth thermal echoes of the early universe. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, this region defies all standard explanations, leaving scientists to grapple with possibilities ranging from cosmic defects to collisions with other universes. At first, researchers dismissed the cold spot as a statistical fluke, a random dip in the data. But as more sensitive instruments like the Planck satellite confirmed its presence, the anomaly became impossible to ignore. The cosmic microwave background, or CMB, is the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang. According to prevailing theories, temperature variations in the CMB should be small and evenly distributed, like ripples on a pond. The cold spot, however, is more like a sudden crater, a departure so extreme it occurs only once in every 10,000 simulated universes based on our current models. So what could carve such a frigid gash into space-time? One leading theory points to a cosmic texturing defect, a relic from the universe's birth called a texture. These hypothetical knots in the fabric of reality, predicted by some grand unified theories, would have formed during rapid phase transitions in the early cosmos. If one of these textures unraveled within the cold spot's bounds, the energy release might have left behind a localized chill. Think of it like a frozen fingerprint pressed into the universe when it was still molten and malleable. Then there's the multiverse angle. Some physicists speculate the cold spot could be a bruise from a collision with another bubble universe, an imprint left by a neighboring cosmos brushing against our own during inflation. In this scenario, the energy exchange between the two universes would have siphoned heat from our CMB, leaving behind a ghostly cool patch. It's a radical idea, but not without precedent. The same quantum field theory that predicts inflation also allows for multiple universes budding off eternally into a greater multiverse. But the most unsettling explanation is the simplest. The cold spot might be a sign of a cosmic void so vast it bends the rules of physics. Supervoids, regions of space with far fewer galaxies than average, can slightly cool photons passing through them via the integrated Sachs-Wolf effect. The problem, to account for the cold spot's intensity, the void would need to be unimaginably large, even by cosmological standards far beyond anything observed in galaxy surveys. Either we're missing something fundamental about how voids interact with light, or the universe is hiding a structure so colossal it rewrites the playbook. What makes the cold spot so tantalizing isn't just its existence, it's the way it exposes the limits of our knowledge. Upcoming telescopes, like the Simons Observatory in Chile, will scrutinize this anomaly with unprecedented precision, searching for subtle polarization patterns or secondary distortions that could crack the case. Whether it's a defect, a collision, or a void, the cold spot is more than a curiosity. It's a cosmic cipher whispering that the early universe might have been stranger, messier, and more spectacular than we ever dared to dream. And until we decode its secret, it remains a frozen question mark hanging in the sky. Nearly a decade after its discovery, Tabby's star, the infamous alien megastructure candidate, still refuses to surrender its secrets. Originally dismissed as a swarm of comets, then sensationalized as a potential Dyson sphere, this cosmic oddball has since spawned even stranger theories. Recent observations reveal its dimming events are growing more extreme, with one 2021 episode blotting out a staggering 15% of its light in just days, like a cosmic dimmer switch flicked by an unseen hand. But the biggest twist, the star isn't just dimming unpredictably. Its entire spectrum is shifting in ways no natural phenomenon should allow. At the heart of the mystery lies the dust. While alien megastructure hype has faded, the replacement explanation, fine, unevenly distributed particulate matter, raises more questions than it answers. Infrared data from the James Webb Space Telescope confirms the presence of silicate grains, the kind you'd expect from pulverized asteroids or evaporating comets. But here's the catch: this dust orbits in clumps so irregular they defy Keplerian motion. Instead of smooth rings or orderly belts, the debris appears to move in jagged, chaotic swarms like a broken conveyor belt spilling its contents haphazardly. Some researchers propose a recent planetary collision where the shrapnel hasn't yet settled into stable orbits. Others wonder if Tabby's star is cannibalizing its own planets, their remains spiraling inward in fragmented arcs. Then there's the star itself. Unlike most variable stars which fluctuate due to internal pulsations or sunspots, Tabby's star shows no correlation between its brightness dips and its magnetic activity. Spectroscopic analysis reveals another anomaly: transient absorption lines suggesting free-floating, ionized gas clouds passing intermittently between us and the star. These clouds don't match the composition of typical circumstellar material. They're richer in sodium and ionized calcium, as if something vaporized a celestial body rich in salts. One daring paper even suggested the spectral lines could hint at artificial spaceborne pollutants, though most astronomers consider that a stretch. The most compelling new theory involves a captured rogue planet. Imagine a Neptune-sized world stripped of its atmosphere by a close stellar encounter, now drifting on a wildly elliptical orbit around Tabby's star. As it swings perilously close during periastron, tidal forces rip away plumes of molten rock and vaporized metal, creating a trailing debris cloud that eclipses the star unevenly. This would explain both the asymmetric dimming and the odd spectral signatures, a sort of cosmic lava lamp effect. Supporting this idea, some models suggest the dips recur every 900 days, hinting at an orbital period. Yet the grandest revelation came in 2023 when astronomers noticed Tabby's star isn't alone. Several other F-type stars in the Kepler dataset exhibit similar, if subtler, irregular dimming. This suggests we might be witnessing a previously unrecognized phase of stellar evolution, where middle-aged stars temporarily gobble their planetary systems due to destabilized orbits. If true, it transforms Tabby's star from a curiosity into a Rosetta Stone for understanding chaotic midlife crises in solar systems. What began as a fringe alien hypothesis has matured into a serious astrophysical puzzle, proving that reality can be stranger than speculation. With every new observation, Tabby's star reminds us that the universe has a flair for the dramatic, and that even the most outlandish mysteries eventually bend toward natural explanations, just not the ones we expected. The only certainty, this star isn't done keeping astronomers on their toes. Most cosmic objects take their time, planets spin leisurely, stars pulse like clockwork, and galaxies rotate over eons. But one white dwarf laughs in the face of cosmic patience. Meet Lamos J02404851 plus 195,226, 9, or J0240 plus 1952 for short. The fastest spinning stellar corpse ever discovered, whirling so violently it completes a full rotation in just 25 seconds. To put that in perspective, if Earth spun that fast, you'd be flung into space like a pebble from a slingshot. This isn't just a record breaker, it's a white dwarf dancing on the edge of self-destruction, stretching the laws of physics to their absolute limit. White dwarfs are typically the quiet retirees of the stellar world, dense, Earth-sized cores left behind when stars like our Sun shed their outer layers. Most rotate sedately, maybe once every few hours, but J0240 plus 1952 is anything but typical. Discovered in 2021, this frenzied object spins nearly twice as fast as the previous record holder, its equator moving at over 300 kilometers per second. The forces at play here are mind-bending. At that speed, centrifugal strain flattens the white dwarf into an oval shape, its equator bulging outward while its poles squeeze inward. If it spun just a fraction faster, it would rip itself apart in a cataclysmic explosion, scattering its remnants across interstellar space. So how did this cosmic top get wound up so tight? The answer lies in a toxic relationship with a neighboring red dwarf star. J0240 plus 1952 isn't just spinning, it's cannibalizing its companion, siphoning off gas that spirals onto its surface like water down a drain. As this stolen material crashes onto the white dwarf's magnetic poles, it transfers angular momentum, accelerating its rotation like a pendulum pushed at just the right moment. But here's the twist, this process should have a natural limit. Theory predicts that at a certain point, the incoming gas should be flung away by centrifugal force, putting a cap on the spin rate. Yet J0240 plus 1952 blows past that limit, spinning faster than any model predicted possible. Some researchers speculate its immensely strong magnetic field, 100 million times more powerful than Earth's, acts like a cosmic lasso, channeling gas directly to its equator and overriding the braking effect. The implications are staggering. If white dwarfs can spin this fast without disintegrating, it challenges long-held assumptions about the tensile strength of degenerate matter, the bizarre quantum pressure-supported material that makes up these stellar remnants. It also raises a terrifying possibility. Could there be even faster spinning white dwarfs out there, teetering on the brink of explosive disruption? Some astronomers now suspect that rare, unexplained stellar detonations called micronova might be caused by these hyper-spinning dwarfs finally crossing their breaking point, their outer layers detonating in localized thermonuclear firestorms. The most haunting detail, J0240 plus 1952's breakneck spin is temporary. Over millennia, magnetic braking and gravitational waves will gradually slow it down like a celestial top winding down on a frictionless table. But for now, it serves as a visceral reminder that the universe loves to defy expectations. Even in death, stars can harbor unimaginable violence, spinning faster than thought possible and daring us to rethink the boundaries of physics. And with every discovery like this, the cosmos whispers a tantalizing question. What other extremes are lurking out there, waiting to shatter our assumptions? Imagine a star so stubborn, so defiant of cosmic rules, that even after enduring the unimaginable violence of a supernova, a blast powerful enough to tear apart entire solar systems. It refuses to die. These are the universe's zombie stars, stellar oddballs that cheat death by exploding only partially, leaving behind a mangled, burning remnant that somehow keeps shining against all odds. And what's even stranger, they're not just surviving, they're thriving, flickering back to life in ways that leave astronomers questioning everything they thought they knew about how stars live and die. Take the case of SN 2014J, a supernova spotted in the nearby galaxy M82. At first, it looked like a textbook type IR explosion, the kind where a white dwarf star detonates so completely that nothing remains. But then, something impossible happened. 3 years after the blast, Hubble Space Telescope observations revealed a faint, stubborn glow lingering at the explosion site. The white dwarf hadn't fully destroyed itself. Instead, it had ripped off its outer layers in a colossal blast while its core survived, wounded but intact, still burning nuclear fuel. It was like watching a building demolish itself, only to find its foundation standing perfectly untouched amidst the rubble. These zombie stars, officially dubbed supernova imposters or type IX supernova, defy the clean classifications of stellar death. Unlike their all-or-nothing cousins, they're the cosmic equivalent of a controlled demolition. Current theories suggest they occur when a white dwarf siphons material from a companion star but fails to reach the critical mass needed for total annihilation. Instead of obliterating itself, it suffers a catastrophic hiccup, ejecting just enough material to create a dazzling explosion while its core soldiers on. The result, a star that's neither fully dead nor fully alive, trapped in a bizarre undead state. But the plot thickens. Some of these stellar survivors aren't content with simply existing, they're evolving. In 2018, astronomers studying the remnants of supernova 2012 Z discovered something unprecedented. The dead white dwarf had not only survived, it had grown brighter post-explosion, as if reignited by some unseen cosmic fuel. The leading explanation is chillingly elegant. The blast might have exposed deeper layers of unburned nuclear material, allowing the star to resume fusion like a phoenix rising from its own ashes. It's a scenario no model predicted, proving that stars can find ways to cheat death we never imagined possible. The most unsettling part, zombie stars might be more common than we thought. Surveys now suggest up to 30% of supposed Type Ia supernova could actually be these partial explosions, masquerading as total stellar deaths. That raises an eerie question. How many other stellar remnants are hiding in plain sight, disguised as ordinary supernova debris? The implications ripple far beyond curiosity. Type Ia supernova are cosmic yardsticks used to measure the expansion of the universe. If some are actually zombie star explosions, our cosmic distance calculations might need a rewrite. What makes these undead stars so mesmerizing isn't just their defiance, it's the way they blur the line between destruction and rebirth. They're cosmic time capsules offering glimpses into the chaotic final moments of stellar existence that no simulation can replicate. And with every new discovery, they force us to reconsider the most fundamental question of all. In a universe where even death isn't always permanent, what else have we gotten wrong about the lives of stars? One thing's certain, the universe has a flair for the dramatic. Just when we think we've seen it all, it sends us a star that refuses to fade to black, a luminous, undying rebel that rewrites the rules right before our eyes. And as telescopes grow sharper, who knows how many more of these celestial survivors are out there, waiting to upend our understanding of life, death, and everything in between. Somewhere in the vast cosmic darkness, an unseen force is reeling us in, an invisible leviathan powerful enough to drag entire galaxies toward it at over 1 million miles per hour. Astronomers call this colossal mystery the Great Attractor, and it's one of the most unsettling gravitational puzzles in modern cosmology. Right now, our Milky Way, along with thousands of neighboring galaxies, is caught in its relentless pull, hurtling through space toward something we can't even see. The first hints of this cosmic tug-of-war emerged in the 1970s when astronomers mapping galaxy motions noticed something bizarre. Instead of spreading out evenly with the universe's expansion, galaxies in our local supercluster were all streaming toward the same patch of sky near the constellation Centaurus. It was like watching leaves floating down a river, only to realize they're all being sucked into a hidden whirlpool. By the 1980s, the anomaly had a name, the Great Attractor. But naming it didn't explain it. This region's gravitational pull suggested a mass equivalent to tens of thousands of Milky Ways, yet when telescopes looked there, they found nothing. Or at least nothing dense enough to account for such a titanic force. Here's where things get stranger. The Great Attractor isn't just invisible, it's obscured by our own galaxy's dusty disk, hidden behind the zone of avoidance, a swath of sky where the Milky Way stars and gas clouds block our view. Infrared and radio telescopes have since pierced this veil, revealing a crowded metropolis of galaxies called the Norma Cluster at the heart of the anomaly. But here's the catch: even this massive cluster is too light to explain the Great Attractor's pull. It's as if we've found a pebble at the center of a hurricane and declared it the storm's sole cause. So what's really anchoring this cosmic undertow? One leading theory points to dark matter, lots of it. The Great Attractor might mark where multiple filaments of the cosmic web intersect, weaving a gravitational knot of unseen matter so dense it bends the motion of galaxies for hundreds of millions of light-years around. Supporting this idea, recent surveys discovered the even larger Shapley supercluster, a behemoth of galaxy clusters roughly 650 million light-years beyond the Great Attractor, whose gravity might be amplifying the pull. It's possible we're caught in a celestial conveyor belt, with the Great Attractor as just one stop on a far longer journey toward Shapley's unimaginable mass. But the plot twists further. Some researchers argue the Great Attractor isn't a distinct object at all, but a statistical illusion caused by our peculiar vantage point. In this view, what we perceive as a coordinated flow might actually be the sum of countless smaller gravitational tugs from all directions, a bit like feeling a breeze that's really the sum of dozens of distant fans. Yet this explanation struggles to account for the sheer coherence of the motion. Too many galaxies are moving too uniformly toward the same spot for it to be random noise. The most mind-bending possibility: the Great Attractor could be a sign of something even larger lurking beyond the observable universe. Cosmologists have long suspected that inflation, the universe's exponential expansion right after the Big Bang, might have left behind density variations so vast they stretch beyond our cosmic horizon. If true, the Great Attractor might be the fingerprint of a structure so colossal we'll never see it directly, its gravity reaching across space-time to nudge us like a shadow hand. For now, the mystery endures. Upcoming projects like the Square Kilometre Array radio telescope aim to map this region's hidden galaxies in unprecedented detail, peeling back the Milky Way's dusty curtain. But the Great Attractor's true nature might remain elusive until we crack the enigma of dark matter itself, the invisible scaffolding that shapes the cosmos. What's certain is this: as our galaxy races toward the unknown, we're not just passive passengers. We're detectives, piecing together clues from a universe that refuses to reveal its deepest secrets easily. And the greatest lesson of the Great Attractor might be humility, a reminder that even on the grandest scales, the universe still has the power to surprise us. Deep within the swirling blue depths of Uranus and Neptune, a storm of unimaginable luxury is brewing, raindrops made of solid diamond, cascading through liquid oceans like glittering hail. This isn't science fiction. It's the bizarre outcome of physics pushed to extremes, where crushing pressures and exotic chemistry transform everyday elements into cosmic treasures. On these ice giants, the very air we breathe would freeze into a solid lattice, crushed beneath atmospheres so dense they blur the line between gas and liquid. And hidden in that chaos, carbon atoms, the same stuff in your pencil lead, are squeezed into the universe's most coveted gemstones. The recipe for diamond rain starts with methane, a simple molecule of one carbon atom bonded to 4 hydrogens that's abundant in both planets' upper atmospheres. When lightning strikes or ultraviolet radiation tears these molecules apart, the carbon atoms are set free, sinking downward through layers of hydrogen and helium. As they descend, pressures mount, reaching millions of times greater than Earth's surface, and temperatures soar to thousands of degrees. Under these conditions, carbon atoms stop behaving like a gas or even a liquid. Instead, they crystallize into diamond structures, forming microscopic gems heavy enough to rain downward through the surrounding fluid. Picture a snow globe, but instead of plastic flakes, it's filled with diamond dust swirling in a sea of electrically conductive ice. Laboratory experiments here on Earth have recreated snippets of this process. In 2017, researchers at the SLAC National Accelerator Laboratory blasted polystyrene, a carbon-rich plastic, with high-powered lasers, simulating the pressures found 2,000 miles below Neptune's surface. For a fraction of a second, they watched as carbon atoms rearranged into nanometer-sized diamonds. But on the ice giants, this isn't a fleeting lab curiosity. It's a planetary-scale refinery where diamonds may grow as large as mountains over millennia, sinking until they hit the planet's solid cores. Some theories even suggest Uranus and Neptune could have entire layers of diamond-rich slush near their mantles, a gemstone veneer thicker than Earth's crust. The real kicker: these diamonds might not stay solid forever. As they plunge deeper, temperatures and pressures could become so extreme that the gems melt into a carbon-rich ocean, a liquid diamond layer sloshing beneath the storms. It's a phase of matter that doesn't exist naturally anywhere on Earth, where diamonds behave less like rocks and more like mercury, dense, conductive, and eerily fluid. This could explain why both planets have such lopsided magnetic fields, wobbling off kilter from their rotational axes. Flowing liquid diamond, threaded with electric currents, might be twisting their magnetic dynamos into bizarre configurations unseen elsewhere in the solar system. What's mesmerizing isn't just the alien spectacle of gemstone precipitation, it's what it reveals about how common such extravagance might be. Exoplanets larger than Neptune, dubbed super-Earths, could have even more prolific diamond rain, their immense gravity creating perfect conditions for carbon crystals to form and fall. Some astronomers speculate that certain carbon-rich worlds might be encrusted with solid diamond mantles, their surfaces literally made of bedrock gemstones. It's a humbling reminder that the universe doesn't play by our terrestrial rules. Down here, diamonds are rare and precious. Out there, they're just another kind of weather. The next time you gaze at Uranus or Neptune's serene blue hues, remember, beneath those placid exteriors rages a world where the sky rains diamonds, where oceans of liquid gemstones churn above cores of fiery rock. It's a place where chemistry becomes alchemy and the ordinary transforms into the extraordinary, one carbon atom at a time. Right now, in the vast emptiness between galaxies, something impossible might be happening. Dark energy, the mysterious force accelerating the universe's expansion, could be flickering like a dying light bulb. For decades, cosmologists assumed this enigmatic energy was constant, woven into the fabric of space-time as a steady, unchanging force. But a growing chorus of observations suggests the unthinkable. Dark energy might be dynamic, its strength ebbing and flowing across cosmic time and space like a phantom whose presence we can only sense when it chooses to reveal itself. The first cracks in the constant dark energy theory appeared in 2018, when measurements of distant supernova, the same stellar explosions used to discover cosmic acceleration in the 90s, showed puzzling inconsistencies. Some patches of the universe seemed to be expanding faster than expected, while others lagged behind, as if dark energy's push were stronger in certain regions. Then came the clincher. In 2023, the Dark Energy Survey released a map of galaxy clustering that revealed eerie voids where the repulsive force appeared weaker, almost as if dark energy had left fingerprints on the large-scale structure of the cosmos. The implications are staggering. If dark energy fluctuates, it could mean we've fundamentally misunderstood its nature. The leading explanation for dark energy, known as the cosmological constant, treats it as an immutable property of the vacuum of space, a kind of background energy that never changes. But if it's varying, even slightly, it might instead be a field like the Higgs, capable of shifting in strength. Some theorists propose it could be linked to quintessence, a hypothetical energy field that evolves over time, growing stronger or weaker as the universe ages. Others speculate these fluctuations might hint at extra dimensions, where dark energy leaks unevenly into our universe from higher dimensional space. The most controversial data comes from quasars. These ultra-bright galactic cores act as cosmic beacons, and their light carries subtle clues about the expansion rate of the universe at different epochs. Recent analyses suggest dark energy was stronger 8 to 10 billion years ago, a direct challenge to the cosmological constant. Skeptics argue these measurements could be skewed by dust or other obscuring factors, but if confirmed, they'd upend cosmology's standard model. Imagine gravity suddenly working differently in different galaxies. That's the level of disruption we're talking about. What's truly bizarre is how these phantom fluctuations might sculpt the future of the cosmos. If dark energy strengthens over time, it could trigger the Big Rip, tearing atoms apart in a final, violent expansion. If it weakens, gravity might regain dominance, collapsing the universe in a big crunch. Almost unsettling of all, it could fluctuate unpredictably, creating pockets of spacetime where physics works differently, islands of reality adrift in a sea of chaos. For now, the debate rages. Upcoming telescopes like the Vera Rubin Observatory and ESA's Euclid mission will scrutinize these anomalies with unprecedented precision. Whatever they find, one thing's clear: dark energy isn't just some abstract number in an equation. It might be alive, shifting in the shadows, rewriting the rules of reality when we're not looking. And if it is, the universe is far stranger and far less predictable than we ever dared to imagine. Gravity doesn't just bend light, it bends time, and nowhere is this cosmic sleight of hand more jaw-dropping than with supernova Rift-Stahl, a stellar explosion so warped by the universe's funhouse mirrors that astronomers watched it detonate 5 separate times across 35 years. This wasn't some glitch in the data or a celestial replay button. It was Einstein's wildest prediction come to life, a single cataclysmic event stretched and fractured across decades by the sheer gravitational might of an entire galaxy cluster acting like a lens. Here's how the cosmic trick works. Between us and Rift-Stahl lies Max J 1149, a gargantuan cluster of galaxies so massive it warps spacetime like a bowling ball on a trampoline. When the supernova's light reached this cluster, the gravity didn't just bend its path. It split the light into multiple beams, each taking a different route around the cluster's dense core. Some paths were longer, some shorter, and just like runners on a twisted racetrack, the light arrived at Earth at wildly different times. The result: a supernova that appeared, vanished, then reappeared again and again, flickering across the sky like a cosmic strobe light. But the real magic lies in the delays. The first 4 images of Rift-Stahl popped up in late 2014, clustered around a single background galaxy. Then, like clockwork, the 5th and brightest echo arrived a full year later, precisely when models predicted. This wasn't just confirmation of gravitational lensing, it was a masterclass in spacetime distortion. The final image light had taken a detour so extreme it lagged behind its siblings by 365 days, proving gravity could stretch time itself on a galactic scale. Imagine watching fireworks where one spark hangs frozen mid-explosion while others fade, only to burst into view a year later. That's the level of surrealism at play. What makes Interstellar truly bizarre isn't just the time warping, but what it reveals about the universe's hidden scaffolding. By reverse engineering the delays, astronomers mapped the cluster's dark matter distribution with unprecedented precision, uncovering invisible mass concentrations that bend light more than visible matter alone could explain. It's like discovering the grooves on a vinyl record by listening to the skips in a song. And lurking in those calculations was an even wilder implication. If gravity can stretch a supernova's light across years, could it also stretch other events? Could we someday observe the same star's birth and death simultaneously, or witness cosmic eras layered atop one another like pages of a book read out of order? The most tantalizing question remains unanswered. Are there other time-lens supernovas out there, their light still winding through the cosmos's gravitational maze? Upcoming telescopes like the Vera Rubin Observatory will scan for these multi-image explosions, turning the sky into a hall of mirrors where past, present, and future collide. Interstellar was more than a scientific curiosity. It was a crack in the cosmic clock, a reminder that the universe doesn't just have history, it plays with it. And somewhere out there, another flicker of warped time might already be racing toward us, carrying secrets from an event we haven't even seen yet, but someday, somehow, we'll see again. From rogue black holes carving trails of newborn stars to diamond rains hailing down on distant ice giants, the universe has proven itself a master of the unexpected. We've journeyed through 25 of the cosmos's most bizarre events, each one defying logic, rewriting textbooks, and leaving even the brightest minds grasping for answers. Fast radio bursts scream across the void with no discernible source. Magnetars crack their crusts in starquakes powerful enough to ripple spacetime. Dark matter hurricanes barrel through our galaxy unseen, while zombie stars rise from their own ashes. And yet, for every mystery we've uncovered, 100 more lurk in the shadows, waiting to append everything we think we know. The true wonder isn't just these phenomena, it's what they reveal about our place in the cosmos. We're standing on a pale blue dot, surrounded by forces and phenomena so strange they'd seem like fiction if the data didn't insist otherwise. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's the beauty of it. Every unanswered question is an invitation to explore, to theorize, to stay relentlessly curious. So what's your favorite cosmic enigma? The hexagonal storm raging on Saturn, the great attractor pulling us toward the unknown, or maybe Tabby's star with its flickering light that still keeps astronomers guessing? Drop your pick in the comments. We'd love to geek out with you. And if these mysteries left you hungry for more, hit that subscribe button. The universe isn't done surprising us, and neither are we. From black holes that shouldn't exist to dark energy's phantom fluctuations, there's always another cosmic curveball just over the horizon. Stay curious, keep looking up, and remember, the next great discovery might be hiding in plain sight, waiting for someone like you to connect the dots. The universe is talking. Are you listening?